Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just take a second and picture volcanic magma.
Oh yeah, the classic mental image.
Right, like you probably immediately think of this thick, glowing red, slowly creeping lava.
Like something you'd see in Hawaii or Iceland.
Exactly. And that image, that whole process, is totally driven by the familiar elements we have right here on Earth. Mainly oxygen and iron.
Yeah, those are the big players for us.
But we need to completely shatter that mental image right out of the gate today.
Oh, absolutely. Throw it right out the window.
Because we are heading to Mercury. It's the smallest, innermost planet in our solar system, but it is hiding this massive, fundamentally alien secret.
It really is. It's just a totally different world.
Yeah, on Mercury, the familiar rules of geology, all that oxygen and iron stuff, it's gone. It's replaced by a chemical reality that is so bizarre, it forces us to basically rethink how planets are even born.
It's wild. It completely flips our understanding of planetary evolution.
So that's our mission for you today. We are going to journey far away from this comfortable Earth-centric view of planetary science, and we're dropping into a world where a totally different element, sulfur, just reigns supreme.
Sulfur is the king on Mercury.
Right. And our goal is to understand how this one single element completely rewrites Mercury's history. It creates a crust and a geologic timeline that looks, honestly, nothing like our own.
Not even close to our own.
And it's so easy, right? It's so easy to just assume all rocky planets are basically variations of Earth. Like Mars is a cold Earth, Venus is a hot Earth.
Yeah, it's the single biggest trap in planetary science, honestly.
I mean, it makes sense why we do it.
Of course it does. We live here. We have naturally built our entire understanding of, planetary accretion, mantle convection, crust formation, all of it. On the chemistry of Earth, Mars, and, Venus.
Because that's what we can see and measure easily.
Exactly. And in those systems, the oxygen fugacity, which is basically just the availability and the chemical activity of oxygen when the planet was forming, that was relatively high.
So there's plenty of oxygen to go around.
Tons of it. Oxygen totally dominates the chemical structure on Earth. It dictates which elements bond together. It decides at what temperature rocks melt. And really importantly, how a planet loses its internal heat over billions of years.
But Mercury is playing a different game.
A completely different game. It formed under entirely different initial conditions in the solar nebula. The rules that govern how magma evolves on Earth, they just fail. They literally fail when you apply them to Mercury.
Because oxygen isn't the boss there.
Right. We're dealing with an environment governed by a completely different primary driver, which is, like you said, sulfur.
Okay, so let's look at the actual data that broke this Earth-centric model, because I think that's fascinating.
The NASA Messenger mission.
Yes, Messenger. Because before Messenger, our understanding of Mercury's surface was pretty much just, educated guessing.
Yeah, we had some flyby data from Mariner 10 back in the 70s, and some telescope observations from the ground, but it was really speculative.
But then Messenger finally gets into orbit around Mercury, and it starts using this X-ray spectrometer.
Which is such a cool instrument, by the way.
It is. It basically waits for solar flares from the sun to blast the planet's surface and then measures the secondary X-rays that bounce off the rocks.
Exactly. It uses the sun as its own giant radiation source to light up the planet's chemistry.
And the chemical signature it beamed back was just shocking. It was entirely incompatible with an Earth-like mantle.
Totally incompatible. It threw everyone for a loop.
It showed that Mercury's crust was incredibly depleted in iron, like missing so much iron, but it was extraordinarily enriched in sulfur.
We are talking about sulfur levels on the surface that are orders of magnitude higher than anything we ever see on Earth.
Which is crazy. And this immediately tells us there's a huge difference in the planet's bulk chemistry. It points to this thing called an extreme reducing environment, right?
Yeah, a highly reduced environment. That's the absolute key to interpreting all this messenger data.
Okay, so help us out here. Break down what it actually means for a planetary body to be highly reduced, because that sounds like a very dense chemistry term.
Oh, sure. So when planetary scientists talk about the redox state of a planet, we're really just talking about the balance between reduction and oxidation when the planet was first clumping together.
Okay.
In an oxidized environment like Earth, Oxygen is super abundant, and oxygen is highly electronegative.
Meaning it really wants electrons.
It loves electrons. It aggressively pulls electrons away from other elements to form oxides. So iron, for example, easily oxidizes to form silicate minerals, and those make up the bulk of Earth's mantle and crust.
So an oxidized Earth is kind of like, well, it's like a rusting piece of iron sitting out in the rain, right?
The oxygen is grabbing onto everything.
That's a perfect analogy, actually. Earth is basically fully rusted.
But Mercury isn't rusting.
No, not at all. Mercury formed way closer to the proto-sun in a part of the early solar nebula where the oxygen fugacity, that availability we talked about, was incredibly low.
So no free oxygen. Almost none. It's the most chemically reduced terrestrial planet we have in the solar system.
Yeah.
In this kind of environment, elements don't lose their electrons to oxygen.
They should keep them.
Right. The whole system favors retaining electrons. So without enough oxygen around to bond with the iron in this big molten protoplanet, the way the iron behaves shifts dramatically.
Okay, but wait, let me push back on this a little bit.
Sure.
We know, as a planetary fact, that Mercury has a disproportionately massive iron core, right? Like, the core is huge compared to the rest of the planet.
Oh, absolutely massive. It's essentially a giant iron cannonball with a thin little rocky shell.
Right. So if it has this giant iron core, how can its crust be so incredibly poor in iron? Where did it all go?
That is the magic of the reduced state.
Yeah.
Because the iron wasn't bonding with oxygen to form light silicate rocks in the mantle, it stayed as unbound heavy metallic iron.
Oh, I see.
And gravity just took over. In a totally molten young planet, all that heavy unbound iron just sank rapidly right to the center.
Wow. So it basically filtered itself out.
Exactly. The extreme reducing conditions caused super efficient planetary differentiation. The iron partitioned almost completely into the core, and it left behind a mantle that was just stripped bare of iron.
That makes so much sense. But that brings up a really big chemical mystery, then.
The sulfur mystery.
Exactly. If the mantle have no iron, but it has tons of sulfur, what is the sulfur doing? Because here on Earth, sulfur is a home wrecker, but it specifically loves iron, right?
Yeah, on Earth, sulfur is what we call a chalcophile element. It has a super strong affinity for iron. It constantly seeks out iron to form these dense sulfide melts.
But if all the iron on Mercury already sank to the center?
Then the sulfur in the outer layers, the mantle, is basically stranded. It's stuck up there without its favorite bonding partner.
So it has to find someone else to dance with.
Exactly. That total absence of iron forces a huge shift in the mineral pathways. On Earth, sulfur and iron get together and form minerals like pyrite, which you know as fool's gold. But on Mercury, the sulfur has to interact with the next best things available. And in this highly reduced, iron-poor molten rock, sulfur starts bonding aggressively with magnesium and calcium.
Magnesium and calcium.
Yeah. And that is a pathway that is almost entirely shut down on Earth. We just don't see it much here. But on Mercury, it becomes the dominant chemical mechanism.
Okay, so sulfur is suddenly best friends with magnesium and calcium. But how does that atomic level chemistry actually change the physical magma? Like, what is it doing to the rock itself?
It completely changes the structural integrity of the magma. Think about how molten rock or silicate melt is built. In a normal Earth magma, the structure is this really complex network of silicon-oxygen tetrahedra.
Okay, silicon and oxygen linking up.
Right. Oxygen acts as the glue, or the bridging ion. It links these structures together into a really robust three-dimensional web.
So it's strong.
Very strong. And that interconnected web dictates everything. It controls how thick and viscous the magma is, its density, and crucially, its liquidus temperature.
The liquidus temperature, meaning the exact point where it stops being liquid and starts forming solid crystals.
Exactly. So if you have all this sulfur-forming complexes with magnesium and calcium on Mercury, it isn't just floating around doing nothing. It actively attacks that silicon-oxygen framework.
It's actively breaking it. Like, okay, think about Earth's magma as a building. The oxygen atoms are these strong steel bolts holding the steel beams together.
I like that.
But on Mercury, because of all this weird chemistry, those steel bolts get replaced by a softer metal.
Yes, exactly.
Like lead or something. So it fundamentally compromises the rigidity of the whole building. It's way easier to collapse.
That's spot on. The sulfur actively substitutes for oxygen in the network.
Right.
Because sulfur is in the same group as oxygen on the periodic table, it can technically fit into those same spots.
It's like an imposter.
A very clumsy imposter. Sulfur is a much larger ion than oxygen, and it doesn't hold on to electrons as tightly. So when sulfur forces its way in and replaces a bridging oxygen atom, it bends the bond angles.
It warps the structure.
It totally warps it. The bond between sulfur and silicon is just much weaker and way easier to break than the normal oxygen-silicon bond. So the melt depolymerizes.
Depolymerizes, meaning it just falls apart.
It breaks up those long, strong chains. Now, a strong, oxidized magma on Earth needs a huge amount of heat just to stay liquid. But if you introduce sulfur and break all those bonds, you're lowering the amount of energy needed.
Which means it stays liquid at much cooler temperatures.
Exactly. The thermal energy required to prevent it from freezing into solid rock drops significantly.
Okay, so that's the theory. But how do we actually know this? Because we haven't brought any rocks back from Mercury.
No, we haven't. And that's where the lab work comes in.
Right, because you can't just run a computer simulation and call it a day. You have to prove it. You have to physically cook a rock and see what happens.
Yeah, you have to subject the exact chemical recipe of Mercury's mantle to the massive pressures and temperatures deep inside the planet.
Which brings us to this mind-blowing research from 2026. This was done at Rice University.
Yes, specifically by a postdoctoral researcher named Yushin Zhang, working in Rajdeep Dasgupta's lab. They wanted to physically replicate early Mercury.
But again, no rocks from Mercury, so they needed a stand-in, a proxy.
And they found the perfect proxy, the Indarch meteorite.
Okay, we have to talk about the backstory of this meteorite because it is just incredible to me that this rock fell out of the sky in Azerbaijan in 1891.
1891, way before we even knew what Mercury really was.
Yeah. It's just astounding. A rock falls from space in the 19th century, sits in a drawer somewhere for 130 years, and now we're using it to simulate an unreachable planet. Why this specific rock, though? What makes Indarch so special?
Indarch is a very rare type of rock called an enstedite chondrite. They make up only about 2% of all meteorites that hit Earth.
Wow, so very rare.
Extremely rare. And their chemistry is key. When we look at their isotopes, like oxygen, titanium, and calcium, they look a lot like the rocks in the Earth-Moon system, which tells us they formed in the inner solar nebula.
Close to the sun.
Right. But unlike Earth rocks, their mineral makeup is aggressively reduced.
There's that word again, reduced.
Right. They're packed with minerals that simply cannot exist if there's any free oxygen around. Minerals like oldamite, which is calcium sulfide, and ninengerite, which is a magnesium iron sulfide.
So this meteorite basically has the exact same weird low iron, high sulfur recipe as Mercury's crust.
It's practically a perfect match for the messenger data. It is a surviving piece of the exact type of material that clumped together to build Mercury.
Okay, so Zhang and the team at Rice University have this piece of the Indarch meteorite, but you can't just stick it in a microwave. How do you simulate the inside of a planet? How do you cook this rock at those kinds of pressures without, destroying the laboratory?
Oh, it requires some serious heavy-duty engineering. They use what's called a multi-anvil press.
Multi-anvil?
Sounds heavy.
It's massive. These machines generate gigapascals of pressure.
Gigapascals, what does that feel like? It's basically equivalent to the crushing weight of hundreds of kilometers of solid planetary rock pressing down on you all at once.
Oh, wow. Okay, so how does the machine do that?
They take the rock sample, powder it, and put it inside this tiny capsule, usually made of graphite or a special metal alloy.
Right.
Then they put that tiny capsule inside an octaequal pressure medium, basically an 8-sided block.
Mm-hmm.
Then massive hydraulic rams drive heavy tungsten carbide anvils together from all sides at the exact same time.
From all sides?
Yeah, so the pressure's perfectly even, simulating depth. And while it's being crushed, a tiny internal heater, like a rhenium furnace, cranks the heat up to thousands of degrees Celsius.
That is insane. Maintaining that kind of heat and pressure without the whole thing just exploding?
The precision is unbelievable. But they have to do it to track exactly when the rock melts and when it freezes. They map the liquidus and the solidus.
It's the solidus being the point where it's totally 100% solid rock.
Right. So they get the rock to the exact pressure and temperature they want, wait for the chemistry to balance out, and then they do a rapid quench.
A quench, like plunging a hot sword into water.
Essentially, yes.
Yeah.
They instantly drop the temperature while keeping the crushing pressure on. It freezes the molten rock into glass in a split second.
So it basically takes a chemical snapshot of what the magma looked like at that exact depth and temperature.
Exactly. And then they slice it open and look at it under an electron microprobe.
And so the big reveal, when they finally looked at these cooked, quenched samples of this Mercury-like rock, what did they actually see? Did the sulfur do what they thought it would?
It did exactly what they predicted. The data was crystal clear. The sulfur aggressively substituted into the silicate network, weakened it, and actively suppressed crystallization.
So the antifreeze theory worked.
It worked perfectly. These reduced sulfur-rich melts stayed liquid at significantly lower temperatures than an equivalent Earth rock would have.
Which brings up that great quote from Rajdeep Dasgupta, the head of the lab.
Oh, I love this quote. He said, "What water or carbon does to magmatic evolution on Earth, sulfur does on Mercury."
It's such a perfect summary, because on Earth, if you add water to hot rock deep underground, like at a subduction zone, it acts as a flux. It lowers the melting point and triggers volcanoes.
Right. The water physically gets into the rock's structure and breaks up the polymers.
Like pouring salt on an icy road.
Exactly. It forces the ice to melt even though it's freezing outside. On Mercury, sulfur is the salt. It's the planetary antifreeze.
But the difference is, water on Earth is kind of localized. It happens at specific tectonic plates. On Mercury, this sulfur is everywhere. It's built into the whole planet.
Yes. It operates globally. It depressed the melting point across the entire mantle of the planet.
Okay, so let's zoom out now. We've got the lab data. We know the atomic bonds are weaker. We know the magma stays liquid at cooler temperatures. How does that atomic level chemistry translate to the huge planet-wide features we see on Mercury today?
Well, if the magma stays liquid longer at cooler temperatures, it drastically extends the lifespan of Mercury's early magma oceans.
So instead of freezing solid quickly, the planet just sloshed around as a giant ball of liquid rock for millions of years longer than we thought.
Exactly. And because the magma had a weaker structureless polymerized, it was also runnier, less viscous.
Like water instead of honey.
Right. And a runny mantle moves heat really efficiently. It convects faster, pulling heat from the core to the surface.
Wait, if it's moving heat to the surface faster, wouldn't the planet cool down faster? That seems like a contradiction.
It does seem like one.
Yeah.
But remember the antifreeze effect. Even though the planet is losing heat rapidly, the sulfur ensures the rock simply refuses to solidify until the temperature drops incredibly low.
Oh man, so it's cooling off, but it's trapped in a liquid state.
Precisely. And this extended period of cooling as a liquid completely changes what kind of rocks eventually form. As the temperature slowly drops toward that new super low freezing point, the very first minerals to pop out of the liquid and crystallize are those sulfur compounds.
The calcium and magnesium sulfides we talked about earlier. Oldamite and 9-ingerite.
Yes. Because they crystallized early while the mantle was still fluid, they were able to concentrate in the upper crust.
Which perfectly explains why messengers saw all that calcium and magnesium on the surface.
Exactly. The entire surface composition is a direct result of this prolonged low-temperature crystallization.
That is so incredibly elegant. It just ties everything together.
It really does. It also explains Mercury's volcanic history.
Oh, right, because Mercury has these huge, smooth volcanic plains, right?
Vast plains of cured lava that sit on top of older, cratered terrain, which means these massive volcanic eruptions happened relatively late in the planet's youth.
But if Mercury was an Earth-like rock, it's so small it should have cooled and formed a thick, solid crust really early. The volcano should have choked off and died.
Exactly. The thermal models for a normal rocky planet of Mercury's size say the volcano should have shut down quickly. But the sulfur kept the engine running. It kept the mantle partially melted and fluid enough to erupt onto the surface long after it should have frozen solid.
Okay, but this leads me to another question, a pushback actually.
Let's hear it.
If the sulfur kept the magma hot and fluid for such a long time, how does that fit with the lobate scarps?
Oh, yes. The scarps?
Yeah. For people who don't know, Mercury is covered in these massive cliffs and ridges called scarps. They look like wrinkles. The planet literally contracted and shrank like a raisin.
A giant iron-filled raisin.
Right, but you can't wrinkle a liquid. If the mantle was fluid for so long, a shrinking core wouldn't cause the surface to snap and form cliffs. The liquid would just adjust. So how did the scarps form?
That is a brilliant point. The mechanics of scarp formation absolutely require a rigid, solid, thick outer shell lithosphere.
Right.
So the timeline is everything here. The global contraction, the shrinking that made those cliffs, it had to happen primarily after the sulfur-rich magma ocean finally cooled past its super low freezing point and locked up.
Oh, I see. So it stayed liquid for a long time, letting the volcanoes erupt. But eventually, even the antifreeze couldn't stop it from freezing.
Exactly. The temperature eventually dropped low enough that even those weakened sulfur silicate networks froze solid.
And once it formed that thick, hard shell...
Once that rigid lithosphere was in place, the massive iron core underneath continued to slowly cool and shrink over billions of years.
And the crust had nowhere to go.
Right. It induced immense compressive stress on the solid rock above it. The crust had no choice but to snap, fail catastrophically, and thrust up over itself to create those huge cliffs.
So the timing of the whole tectonic history is dictated by the atomic behavior of sulfur.
Yes, down to the very atoms. And it goes even deeper. It affects the magnetic field, too.
Wait, really? The sulfur in the rocks affects the magnetic field of the core?
Oh, absolutely. Mercury has a global magnetic field generated by a churning, convecting liquid iron core, a geodynamo.
Just like Earth.
Just like Earth. But for a geodynamo to work, you need a very specific rate of heat escaping from the core into the mantle. If the mantle acts like a thick thermal blanket, the core stops churning and the magnetic field dies.
But we just said the sulfur made the mantle runnier and more efficient at moving heat.
Exactly. By proving that the sulfur-rich mantle stayed fluid and less viscous for longer, the researchers basically rewrote the equations for how heat moves across that boundary. The chemistry of the rock directly controlled the cooling rate of the iron core.
Which means the sulfur literally dictated the strength and the longevity of the magnetic field we still measure today.
It's all connected. The microscopic chemistry of the rock is inextricably linked to the massive geophysical engine inside the planet.
That is just phenomenal. It's a cohesive, start-to-finish explanation for every weird thing about Mercury. The surface chemistry, the extended volcanoes, the cliffs, the magnetic field, it all tracks back to sulfur.
It's a total paradigm shift, and it really validates the incredible work done by the Rice University team.
Supported by NASA grants and the Rice Space Institute Center for Planetary Origins to Habitability, which, is a long name, but they are doing vital work.
Vital work because, honestly, this goes way beyond Mercury.
Yes. This is what I really want to get into. Why does this single case study matter for the rest of the universe?
Because it exposes our severe terrestrial bias.
Our Earth-centric trap.
Exactly. Because we live here, all our instruments, our math, our thermodynamic assumptions, they are all grounded in the oxidized, iron-rich chemistry of Earth.
So when we look at other planets, we just assume they're built the same way.
We project our local rules onto the rest of the galaxy. And Mercury just proved that if you apply an oxidized model to a highly reduced planet, you get totally wrong answers. You predict the wrong thermal history, the wrong structure, everything.
And we are discovering so many planets right now.
Thousands of them. With advanced telescopes like James Webb, we aren't just finding rocky exoplanets, super-Earths, and sub-Neptunes. We're actually starting to look at their atmospheres and figure out what they're made of.
And they aren't all like Earth.
Not at all. Many of them orbit stars with totally different chemistry in primordial disks that are vastly different from our own. Statistically, a huge number of these rocky exoplanets formed under highly reduced conditions.
Meaning the universe is likely just teeming with these sulfur-dominated iron-poor worlds.
Absolutely teeming with them.
Which is kind of ironic, right? By turning our focus inward to the absolute smallest, closest planet to our sun, we've basically built a decoder ring to understand the farthest, most alien exoplanets in the galaxy.
That's a great way to put it. Because if we look at a distant super-Earth through a telescope and try to model its interior using Earth math, we will fail.
We'd calculate the wrong melting points, the wrong crust thickness.
The wrong timeline for when it might release gases into an atmosphere. We would completely misunderstand its capacity to be a stable, maybe even habitable environment.
But thanks to the data from crushing that little Indarch meteorite,
we now have the actual thermodynamic framework. We have the correct phase boundaries to model the geology of reduced exoplanets accurately.
It's incredible. It lets us predict when a sulfur-rich planet light years away will solidify, when its volcanoes will stop, and how its crust will deform.
We can anticipate that its surface might be covered in oldmite instead of basalt. We can adjust our models for its magnetic field. We are learning how to read the geological history of worlds we can't even see clearly yet.
It's just a remarkable progression of knowledge. To summarize this whole journey, we started with one anomalous, weirdly reduced rock that fell in Azerbaijan in 1891.
The Indarch and statite chondrite.
Right. And by recognizing that its chemistry matched the weird data from Mercury, researchers in 2026 used it as a proxy. They subjected it to gigapascals of pressure and thousands of degrees of heat.
They mapped the phase boundaries of a sulfur-rich mantle.
And proved that sulfur acts as a planetary antifreeze. It depolymerizes the melt, lowers the energy needed to stay liquid, and pushes the freezing point way down.
Which subsequently rewrites the entire geological timeline of Mercury. It explains the sulfide crust, the long-lasting magma oceans, the late-forming scarps, and the magnetic dynamo.
And more importantly, it proves how much our understanding of the universe is biased by our own backyard. Sometimes, just swapping out one single element, oxygen, for sulfur can rewrite an entire planet's history.
It changes the architecture from the atomic scale all the way up to the global features.
Which leaves us with a really provocative thought to end on today. We now know the profound consequences of swapping oxygen for sulfur, but sulfur is just one variable.
Just one of many.
Right. As we keep looking at distant star systems, we are going to find protoplanetary disks with entirely alien elemental recipes. If a relatively simple swap like sulfur can create a world as bizarre as Mercury, what else is out there?
The possibilities are endless.
What happens to a planet's mantle if it's heavily enriched with carbon? How does a planet dissipate heat if it's dominated by exotic refractory metals? What kind of wild, unpredicted rocks are currently shaping worlds where the initial chemistry forces elements into configurations we haven't even thought to synthesize in a lab?
It's mind-boggling.
Mercury is proof that our familiar Earth chemistry is just one specific lucky outcome in a universe that is capable of building planets through an almost infinite number of distinct alien pathways.